Have you ever seen a complicated circuit diagram and thought, how can anyone figure out the current or voltage in there? Well, in simple circuits, we use Ohm's law and combine resistors in series and parallel. But when circuits get complicated, with many loops and branches, we need something more powerful. That's where Kirchhoff's rules come in. These rules are based on two fundamental principles: first, conservation of electric charge, and second, conservation of energy. Kirchhoff's rules help us calculate unknown currents, which we represent with capital I, and unknown voltages, represented with capital V, in any electric circuit, no matter how complex it is. For example, in a cube-shaped resistor network, where no two resistors are in clear series or parallel, Kirchhoff's laws are the only way to analyze the current flow. Let's begin with Kirchhoff's current law, also called the junction rule. Law statement: at any electrical junction, the total current entering the junction is equal to the total current leaving the junction. Mathematically, this is written as summation of I sub in is equal to summation of I sub out. Now, let's break it down with an example. Suppose two currents, capital I sub 1 and capital I sub 2, flow into a junction, and one current, capital I sub 3, flows out. Then, we write I1 plus I2 equals I3, that is, I sub 1 plus I sub 2 is equal to I sub 3. This follows the law of conservation of charge. Charge cannot pile up at a point in the circuit. This rule must be applied at every point in the circuit where multiple conductors meet. Next, we have Kirchhoff's voltage law, also known as the loop rule. Law statement: the algebraic sum of all potential differences in a closed loop is equal to 0. This is based on energy conservation. If you follow a charge around a complete loop and return to the same point, the total energy change must be 0. In formula form, summation of delta V equals 0. Now, how do we apply this? We assign a sign to each voltage term based on the direction we move around the loop. When we go from negative to positive through a battery, it's a voltage rise, so we write plus epsilon. When we go in the direction of current through a resistor, it's a voltage drop, so we write minus I multiplied by R. So, in a loop containing one battery and two resistors, the equation might be epsilon minus I multiplied by R1 minus I multiplied by R2 equals 0. That's how we apply the loop rule, by summing all the voltage changes and setting the total equal to 0. Now let's learn how to systematically apply Kirchhoff's rules to a circuit. Step 1. Label all the currents with arrows. Call them I1, I2, I3, and so on. Step 2. Apply the junction rule at every junction. That gives you equations relating the currents. Step 3. Apply the loop rule to each independent closed loop. That gives you equations involving voltages and resistances. Step 4. Solve the system of equations to find the unknown currents. By combining both rules, you can solve even the most complex circuit, whether it's a power grid or a circuit board. Let's work through a real example, the same one shown in figure 3.15 of your NSERT textbook. We have two loops and three branches. Let's define current in the first loop as I sub 1, current in the second loop as I sub 2, current through the shared middle branch as I sub 3. Step 1. Apply the junction rule at node A. I sub 3 equals I sub 1 plus I sub 2. Now, apply the loop rule to the first loop, labeled AHDCBA. We get negative 30 multiplied by I sub 1 minus 41 multiplied by I sub 3 plus 45 equals 0. Now, apply the loop rule to the second loop, labeled AHDEFGA. We get negative 30 multiplied by I sub 1 plus 21 multiplied by I sub 2 minus 80 equals 0. We now have three equations. Capital I sub 3 is equal to capital I sub 1 plus capital I sub 2. Let's wrap up with a quick recap. Kirchhoff's current law, also called KCL, at any junction, the sum of currents entering equals the sum of currents leaving. Formula: summation of I in equals summation of I out. Kirchhoff's voltage law, or KVL, in any closed loop, the total voltage change equals 0. Formula: summation of delta V equals 0. These two rules are not just academic, they're essential tools in every field involving electricity, from designing power grids to analyzing electronic circuits to building the motherboard inside your computer. Without Kirchhoff's rules, we couldn't solve most real-world electrical problems. I hope this helped you build a solid understanding of how current and voltage behave in even the most complicated circuits. See you in the next class with another exciting concept from the world of physics.